I have you loud and clear.
Hello. Welcome. Science.
And that is to say,
physics, medicine, nature,
or
Space. Time.
the brain,
Life. The universe.
Hello, welcome to The Naked Scientists. This is the show where we bring you the latest breakthroughs in science and technology. With me, Chris Smith, and with Adam Murphy.
This week, we are taking a look through the window, or rather, at the window. We are looking at glass. Coming up, how do you make glass? How does stained glass work? And is bulletproof glass really bulletproof?
And in the news, why birds might be in big trouble, swimming the channel, scratching an itch, and are we on the verge of a cure for the common cold?
The Naked Scientists podcast is powered by ukfast.co.uk.
Now, last Friday, millions of people united around the globe to campaign for action on climate change. There is significant concern about what's happening to the environment and the world's flora and fauna.
And we need to worry, because many species are coming under significant pressure. For instance, if you go down to the woods today, most likely from all directions, you'll hear sounds like this. But if present trends continue, it could end up sounding more like this.
Indeed, and Ken Rosenberg is at Cornell University in the US, where he's been studying bird populations and habitats, and his latest findings should certainly put the cat among the proverbial pigeons.
This study is showing a staggering loss in the abundance of birds all around us in North America. We're seeing about a 30% loss in the total number of birds out there since 1970. That's a loss of 3 billion birds, which means that our best estimates is that there were about 10 billion breeding birds in 1970 and about 7 billion birds today.
And if you stratify by all the different species, who are the biggest losers, or is everyone the loser here?
Well, we saw large losses in almost every habitat group. The biggest losers are probably grassland and farmland birds, because they showed the largest proportional loss, more than half of their population gone since 1970, and also the largest absolute loss, about 700 million birds from their population was lost. But there were smaller levels of loss in almost every habitat.
Were there any winners? Did the numbers of any rise to compensate?
There were. So in North America, where most of the conservation investment has been is in waterfowl and wetland birds, and that showed up in the data. The wetland bird group was the only group to show an increase. Waterfowl populations have more than doubled in that same time period since 1970, and that's because of the investment in wetland restoration, waterfowl management, primarily for recreational hunting.
I'm intrigued to know how you actually have managed to count 3 billion birds.
We used a lot of different survey data sources. Because there are so many bird watchers out there, we have a lot of eyes and ears, and by organizing standardized surveys that use volunteer birders to count birds, 400 species are covered pretty well by this breeding bird survey. And then we brought in other surveys, such as the Christmas bird count, to look at birds that we only see in the winter. So basically, we put together the best information we had for each bird group.
But in the paper, you also talk about using radar.
Right. Weather radar gives you a picture of the total mass of birds that are migrating over the continent at any given time. And these birds are flying at night. And so the radar is picking up the total biomass of their migration at night. And by looking at that number over time, so over an 11-year period, we saw a reduction in the total biomass of migrating birds that was about the same magnitude of decline as we were seeing in the survey data. So two completely independent methodologies and data sources were showing the same result.
What do you think the mechanism underpinning all of this is? Do you think there's one single mechanism, or do you think there's a range of factors here?
Well, it's definitely a range of factors. We have a pretty strong sense that habitat loss and degradation is the primary driver for most groups of birds. But there are many things that kill birds that are human-caused, and they range from pesticides, cats, windows, collisions with buildings and towers. There's lots of different drivers. Pinning them down to the specific decline of any species is very difficult to do, and that's really the next phase of our research.
I'm very alarmed by the scale of these figures, not just the scale, but how quickly this has kicked in. And the reason for asking the question about what you think the mechanism is that, well, if we're going to try to arrest that decline, we need to know what's causing it. And it doesn't sound like you've got a clear picture on that yet. So it's going to be really, really hard to get a handle on this. And perhaps it's too late already, would you say?
Well, I don't think it's too late for most groups. And we do know that bird populations are very resilient. And we have this model from wetland and waterfowl to guide us. We know that with bald eagles and other raptors, when we saw a problem with DDT and were able to ban those pesticides and stop those birds from being shot, their populations did rebound. And so we need to replicate those successes. So in grasslands, we need some changes in agricultural policy that allows there to be some native grassland on the habitat. And agriculture has become so intensive that it has just squeezed birds off the landscape, where even 10, 20 years ago, there were more birds that we were able to live side by side with. So it's going to take a lot of different actions at the individual level, at the societal level, but we are hopeful because we know that this has worked in other cases.
You've got this in North America, but do you think this is, it's a horrible analogy, but the canary in the coal mine for what's going on in geographies worldwide? If I did the same sort of study in Europe or in Russia or in Australia, would I see a similar trend?
Absolutely, and these papers are coming out one after another about declines in birds in Europe, declines of insects globally. This is a global phenomenon. The loss of biodiversity, the loss of species, the loss of abundance. So the canary in the coal mine analogy is exactly correct today. This is telling us that there is something dreadfully wrong in our environment. We can see what's going on with birds because they're so conspicuous and we can count them. So we can be sure that what it's telling us is that these things are going on with other groups as well, and that we're seeing an unraveling of ecosystems and a degradation of the health of our overall environment. It has to be happening if the losses are so pervasive as we're seeing.
Terrifying, isn't it? Imagine if 1 in 3 humans just disappeared over about a 30 or 40 year period. That's roughly what's happened to the bird population in North America. And if what Ken is saying is true, in fact, all over the world. That was Ken Rosenberg that you were listening to, and the paper that was describing those results has just come out in the journal Science, if you want to catch up with it.
Now, from flying birds to swimming people, Sarah Thomas set a new world record this week when she became the first person to swim the English Channel 4 times over non-stop. She was in the water at 18 degrees Celsius and swimming constantly for 54 hours. Phil Sansom has been finding out how she accomplished it.
Just after dawn on Tuesday morning, Sarah Thomas staggered onto Shakespeare Beach in Dover and became the first person ever to swim the channel 4 times, non-stop. Sarah is an American long-distance swimmer, 37 years old, and a survivor of breast cancer. Now, the year after she's finished her treatment, she has set a world record. How did she do it? How did she bounce back from cancer therapy to spend more than 2 days in nail-bitingly cold water, swimming what was supposed to be the length of 3 marathons, but thanks to strong tides, ended up being closer to 5? Well, it's partly thanks to physiology. Sarah had a number of challenges to face on her swim, the first of which is energy. She kept her calories up by drinking from a protein recovery drink every half an hour. But to use those calories most efficiently, she needs a certain type of muscle called type 1 or slow twitch muscle. It's red muscle, the kind that gives you dark meat from a turkey. Unlike type 2 fast twitch muscle, slow twitch muscle is really good for endurance because it's really good at using oxygen. It has a high blood supply, it has little molecules called myoglobin that take the oxygen out of the blood, and it has lots of mitochondria for turning that oxygen into energy. Perfect for long-distance exercise, and with training you can turn more of your muscle fibers into that helpful type 1. The second challenge she faced was the cold. Christoph Schweening is a physiologist from Cambridge University who was pretty impressed with this feat.
If I were to fall into the English Channel, I wouldn't survive for more than about an hour or so. So how is it that Sarah managed to survive for 54 hours in water close to 18 degrees C? Well, what Sarah has managed to do is minimise the extent and consequences of the hypothermia she will have suffered during the swim.
She didn't even wear a wetsuit, only a cap, goggles, and a swimsuit. She had to have trained her body to avoid losing heat wherever possible.
The major adaptation that minimises heat loss is simply keeping the warm blood away from the cold water, and that occurs through the restriction of blood flow to the skin and the presence of a relatively thick layer of subcutaneous fat. Both of these are not unique to Sarah, but what Sarah seems unusually good at is maintaining a continuous high heat output, even when her core body temperature has fallen to a level where most of us would be a shivering wreck. Part of that ability is her aerobic fitness, with an ability to continuously metabolise fuel. But she must also have managed to train out her shivering response. Shivering is counterproductive when swimming, and this is a well-known adaptation in people who are routinely exposed to the cold.
All of this meant that she coped surprisingly well with the cold. She actually said the worst part may have been the salt water, which dried out her mouth and throat. And she even got stung by a jellyfish. Through all of it, she kept going.
So I suspect that Sarah physiologically is not really that unusual. Sarah's real strength, though, comes from her ability to focus her mental effort on continuing to put one arm in front of another, even when the most simple mental task becomes almost impossible. Now that requires practice and stamina that few are able to muster.
Christoph Schreining from Cambridge University commenting on that amazing achievement of Sarah Thomas, who swam the Channel 4 times non-stop earlier in the month.
A brand new podcast looking at gaming news.
They won't be playing games on this course. That's not to say that we don't have an incredible array of equipment that they can use all in their free time.
Reviews.
Spending notifications, no. If it says you need an update, I'm going to flip out.
And Retro Revival.
Yay! It's hatching. With Chris Barrow
and Lee Milner.
The Naked Gaming Podcast. There's a brand new episode out now, wherever you get your podcasts.
Most of us succumb to an average of 3 coughs and colds every year. The main culprits in over half of these cases are viruses called rhinoviruses and enteroviruses. And when a symptomatic person sneezes, they spray out a mist of millions of these particles that drift about in the air waiting for you to breathe them in. Once they settle on the cells in your nose and throat, they invade, hijack the cells and transform them into virus factories. And then that cycle starts all over again, making you feel awful in the process.
But now, scientists in the US have identified a protein in our cells that these viruses rely on when they grow. And cutting off the supply of this substance halts the viruses in their tracks. So could this potentially pave the way for a cure for the common cold? Cambridge University virologist Ian Goodfellow took me through the results of the new study.
In this paper, they've essentially identified a host protein that appears to be essential for a number of viruses that cause the common cold and enteric infections. When they've deleted this gene encoding this particular protein, the viruses are no longer able to infect cells.
How did they find the gene in question?
To identify the gene, they used a process to delete every single gene in the human DNA.
Is that what, one by one? So they go through the entire genome and one at a time disable one gene after another and then test whether or not that disabled gene has an effect on the virus?
Exactly that. So you mutate every single gene one by one, and then you infect them with the virus. And then you look for cells that survived, and these cells that survive are resistant to infection and therefore have a mutation in a gene that is essential for the virus life cycle.
Right, so they identified a gene. What is that gene that they've found that seems to be so important? And do they know why disabling it has this effect on the virus?
The gene itself is called SETD3. It's a protein known as a methyltransferase. And they don't know exactly what stage in the virus life cycle it plays its role, but they know that in the absence of this protein, the cells are largely completely resistant to infection.
They show that in the dish to start with, but would that work in a living animal? Because it's one thing to disable a gene and have a cell still thrive in a dish, but very different with a whole animal in which you were trying to do this.
And this is one of the beauties of this particular publication. They've translated their observations from immortalized cells into a whole organism model. So they've taken a mouse model and they've inactivated this gene and shown that when you infect these mice with these various viruses, they're completely resistant to infection.
And clinically, what's the relevance or use of this discovery? How could virologists now take this forward, and is it potentially a doorway towards, I hate the phrase, but a cure for the common cold, or at least some forms of the common cold?
So what this paper does is it really identifies a key host cell protein that's important for a whole group of viruses that cause a range of diseases. It isn't immediately like tomorrow we can all of a sudden develop a drug to this particular protein, but what it does is it says if we find a way to modify the function of this protein, then we probably have an effective way of treating or controlling or preventing the infection by these viruses. So it identifies SETD3 as an essential component in the virus life cycle, and if you can make drugs that target SETD3, you might be able to inhibit the virus replication.
Could the same strategy be used for other clinically relevant infections? Because colds are one thing, they're a nuisance, but they're not by any means the main way in which viruses bring down the human race.
Yes, exactly, and it's become increasingly common in virology now for individuals to use this precise approach where you use CRISPR-Cas screening to identify host proteins that are essential in a virus life cycle, and then to use that as a potential target for therapeutic approaches. And just recently, we've undertaken some work on a related family of viruses known as noroviruses that cause gastroenteritis to do precisely the same type of approach. And when we've done that, we've done a CRISPR-Cas screen to identify a single protein known as G3BP1. This protein is absolutely essential for both the mouse norovirus replication and for human norovirus replication. And we hope that in the future this will enable us to develop a potential therapeutic approach for the control of norovirus-induced gastroenteritis.
Viruses are notorious for being able to change their genetic makeup. They mutate or change. If we did work out how to use these vulnerabilities to make drugs to block them, is there not a high likelihood that pretty quickly the viruses would fight back by just adjusting their modus operandi to bypass whatever block we put in the way?
This point about the development of resistance to drugs is a real key factor when we consider developing any sort of therapy for viruses. And as you say, viruses change very rapidly. But when we target a host protein, it's very, very difficult for the virus to change to overcome that. It's not impossible, but it's much easier for a virus to develop resistance to drugs that target viral proteins than it is for it to develop resistance against drugs that target the host.
So there is hope on the horizon for coughs and colds and possibly puke bugs as well. Thanks very much to Ian Goodfellow from the University of Cambridge. The study he was commenting on there is by Jan Carrett and his team, and it just came out in the journal Nature Microbiology. Now, earlier this month, a very special scientific award show was held at Harvard. That was the 29th annual Ig Nobel Prizes. But what science could deserve such an accolade?
On the 12th of September, the most prestigious award show was held, the Ig Nobel Prizes. Only the best of science gets awarded these prizes. This year, they went to groundbreaking work, such as showing that a pizza may protect against illness and death if that pizza is made and eaten in Italy, for a better understanding of cubic wombat poo, and for an estimation of the amount of saliva produced by a 5-year-old. Okay, so maybe not what you'd think about at first glance, but the Ig Nobels go to science that make you laugh and then make you think. Science that may sound quirky but has importance behind it. One of this year's winners was Francis McGlone from Liverpool John Moores University, who, along with Gil Josipovich and others, examined the pleasurability of scratching an itch. You know that feeling when you've got an itch and you just have to get to it, and then the relief of finally getting rid of it. Francis spoke with me about the work he's done.
In this experiment, we looked at different body parts to see where itching was most accompanied by pleasure, basically. So we looked at these 3 different body sites and asked people, after we'd made them itch, which one was the most rewarding. And I think it was the quirkiness of that experiment that attracted Ig Nobel. But underneath this almost sort of obvious sort of question about why do you want to scratch an itch, there's an underlying question of why, when you scratch that skin, is it so rewarding? And this is what really interested me, because the skin that you've just scratched, if you scratch the skin when it's not itchy, it's actually quite uncomfortable. But once we create an itch, scratching that skin site again becomes absolutely deliriously rewarding.
But as I've mentioned, the Ig Nobels have to make you think. They can't just be quirky. So what does this work make you think about?
This research has clinical implications as well, because chronic itch is a condition where patients just cannot ignore scratching a piece of skin until it's quite often damaged. So that itch-scratch cycle is a clinical feature in many chronic itch conditions. Most people appreciate chronic pain conditions and can have some sympathy with people suffering from pain, but itch doesn't really get the kind of credibility it needs, I think, in terms of how debilitating it is for people. A good example I had was a patient who had his foot blown off on a landmine, and this often results in a phantom pain from that missing limb. What this patient claimed of was a phantom itch between the big toe and the toe next to it. So he had itch coming from a foot that wasn't there. And I think most people can appreciate just how devastating that can be to not be able to get at an itch. So again, we need to look at underlying mechanisms as to why itch is so pervasive, why it cannot be ignored, and in clinical conditions, how best we can treat chronic itch. And of course, with all of these interesting questions, first of all, we need to understand the mechanisms, and then we're in a better position to try and treat such conditions.
And there's a good chance, just after hearing that, you're now a bit itchy. But when all is said and done, and all itches have been scratched, and the prizes given out, where does Francis think the Ig Nobels fit into the world of science?
I think the Ig Nobel Prizes have been running for quite some time now, and they really do add a very important element to us as scientists in terms of getting outreach or enabling us to tell our stories to wider audiences. All Ig Nobels are based on good science, but a bit wacky. I think that opens the door to drawing audiences in that may not have necessarily be interested in our areas of science, but they're drawn in by the quirkiness, and then of course underneath that they get exposed to the basic science questions that are being answered and asked within these research areas. And I think the Ig Nobel provides an absolutely superb mechanism by which the general public or the wider public can become aware of the kind of things we do as scientists.
And the answer to the most gratifying body part to scratch, apparently according to Ig Nobel itch investigator Francis McGlone, is the ankle.
I didn't get that. Did you get that? Would you have picked that?
I mean, the sock line on your ankle, that can be real good to scratch at the end of the day.
Yeah, I just wonder if it's because, by and large, the most commonly bitten body part for mosquitoes to target is your feet.
Oh, yeah.
Partly because the molecules that come off the sweaty socks are very attractive to mosquitoes, so they tend to make a beeline, if that's the right phrase to use, for your feet. And it might be that you get so many mosquito bites, they are just delicious to scratch in the foot area, and that might be why. Maybe his results are a bit confounded. He needs a follow-up study to look at that. Anyway, we better move on. We're on to the mailbox now. This is the part of the programme where we read out your correspondence. Now, Peter Bridger has got in touch from Australia. He sent us a very nice letter. It went actually all over the place before it finally arrived to us. I'm sorry we're coming to this slightly late, Peter. But he's been in touch telling us about the time that he spent here in Cambridge, because he was originally working with centrifuges. And this got him thinking and wondering about gravity. And so he's proposed an experiment. And he says, well, could you take a gold bar all over the world and measure the gravity that it feels at the equator compared with the poles? And the rationale behind this idea is that because the equator is spinning a lot faster than the poles are, then the bar ought to weigh a bit less there, apparently, because it's not being flung out to space at the poles in the same way as it is at the equator. Adam, is that a good idea?
I think it is. I mean, the first thing to say is we're not going to get flung off the planet like some horrifying roundabout. Gravity is much, much stronger than any spinning the Earth does. But it's a very good experiment because it's one that's been done a lot throughout history. And they've found that in different parts of the world, gravity actually is different. And they found that it can waver by up to about 0.5% of how heavy something is. So in cities like Kuala Lumpur or Singapore, which are by the equator, something is 0.5% lighter than it is in places like Oslo, because that's at the poles.
Pretty extreme way to go on a diet, though, isn't it? To go down to the equator just to lose a bit of weight.
I mean, if that's what you got to do to make yourself feel better about the scales, that's what you got to do.
So it has been done.
It has, yes. Not only have they gone to these places with weighing scales, because that's how you measure how much something weighs, we've had satellites in orbit measuring these things. That's
GRACE, isn't it? The pair or brace of satellites that actually whiz around the Earth and measure how fast one's accelerating relative to the other. Because that's how they weighed the ice on Greenland to know what the rate of ice retreat was.
Yeah, it's the Gravity Recovery and Climate Experiment is GRACE. And when one of them passes over somewhere heavy, it gets pulled a bit ahead and then the other one catches up, and that's how it measures things.
Thank you very much, Adam. Meanwhile, a quick shout out to Rob Clements. Now, he's in Nottinghamshire and he's one of a very select band of brothers, if I can put it like that, because he's completed the audio equivalent of an Iron Man challenge, because he's made it through our entire Naked Scientist podcast catalogue, close to 1,000 episodes, going back to the very beginning. We're one of the oldest and longest continuous running podcast in existence, so that's quite a feat. He has now reached August 2019. So, Rob, that red tape is in sight. You're almost up to date. You're almost back in sync with the programme. We're very intrigued to know if anyone else has managed a marathon like this. So if you're one of that band of brothers, do let us know. Write in to chris@thenakedscientist.com. And indeed, if there's anything else you'd like to ask us to cover here on the mailbox, drop us a line. We'd love to hear from you.
The Naked Scientists podcast is produced in association with Spitfire, cost-effective voice, internet and IP engineering services for UK businesses. Find out how Spitfire can empower your company at spitfire.co.uk.
Music in the programme is sponsored by Epidemic Sounds, perfect music for audio and video productions.
This is The Naked Scientists with Chris Smith and with Adam Murphy. And in the next 20 minutes or so, we're now going to get crystal clear, we hope, about the world of glass, including finding out what it is, how we make it, and how we endow it with some very special properties.
First up, when a chemist wants a giant test tube or a Harry Potter movie wants some fancy-looking glassware for an apothecary scene, who would they turn to? The answer is often Glass Solutions in Ely, and Phil Sansom's been to see their technical lead Ryan Wood and to have a go himself.
Okay, so this is one of the largest items that we make. It's a 50-litre vessel, 3 layers of glass. Chemical reactions will be going on in the inside. And then there's 2 more jackets on the outside. One of them's to keep it to the correct temperature that it needs. And the third jacket is just a vacuum jacket, just so there's no heat loss.
This is obviously a long way from the big glass tubes that are the raw material that I just saw. Can you take me through how you get from that to this?
There are lots of methods that we use. We would take the cylinder glass out and put it in one of our lathes.
And a lathe, to clarify, what is that?
So it's just a big machine that holds and then turns the glassware. The working temperature of glass is around 1100 degrees, so we have to take it up to around 1100 degrees before we can start moving the glassware around.
What happens to the glass when you actually heat it up? What does it do to it?
We just melt the glass. It makes it malleable, so we can move it. And then as soon as it goes under a certain temperature, it stops moving. So we have to keep everything up to the right temperature. And there's lots of other factors that we have to do. So we have to worry about stress, glass stress. When we work the glass, it's trying to pull itself apart. So we have to get that glass into an oven as quick as we can before it breaks. The glassware needs to go in an oven at 565 degrees.
So are you saying that if you don't get it in the oven in time while it's cooling down, it'll be under too much stress and it'll shatter?
Yeah. If we was to put this glassware on the side, as it's cooling down, the glass will fall apart.
This oven process is called annealing. And what's going on is that at 565 degrees, you get microscopic flow in the glass. And that tiny amount of flow means that little points of stress within the structure of the glass get smoothed out. It's the final stage of a hard day's work here.
All of the glassware that we do here is handmade. The lathes are the only machinery that we have, and we need the lathes. Other than that, everything is handheld. We have graphite rods that once the glassware's warm, we'll use the graphite rods to move the glass around, and we have other tools as well. On each of our lathes, we have a series of different flames.
I can see some of the jets, I think, right now.
Yep.
Oh, they look so scary.
Yeah, so this is what we call a whisper jet. Our large one is called a pepper pot. It's a very, very large flame. This hand torch here, we have a flame that comes out of it, maybe a 30mm flame, propane and oxygen mix. So it's a very, very, very hot flame.
What that means is like a bright blue flame right in front of me.
Yeah. We can get a lot longer flame. Depends on what we do. We can get to 2 to 3 foot. It's very, very noisy and very, very hot.
I'm genuinely frightened.
Yeah.
Where does the actual blowing come in?
If we want a round end in a tube, we'll need to connect a pipe from our mouth through the lathe into the glassware, and then we'll heat the glassware up, and then we'll gently blow the glass into the shape. Virtually everything that's under a 20 litre, we will blow the glass.
At this point, Ryan let me have a go. I was ready for this. How hard can it be? You just heat one end of the tube, then blow down the other.
Keep this end, touch this end, okay?
Yeah.
That's fine, leave it like that. That's fine. So that is very thin.
Ooh.
Yeah, that is very thin. So you can
almost popped then, didn't it?
Just so you can see how flexible glass can be.
It really went at the end.
Yeah.
Bloody hell.
Yeah. If you blow too hard, it'll pop into a million pieces.
How'd I do for a first time?
It's good. Yeah, absolutely.
Okay, so maybe it's harder than I thought. Ryan was struggling to say nice things about my attempt, so I decided to move on. How hard is it to learn to make something this big? Because that's like a big 50-litre thing.
A big vessel. So it's always been said that it's going to be absolute minimum of 5 years of training to get to a certain level. To get up to this size vessel, it will take around 10 to 15 years. It's very hard to see and understand what the glass and predict what the glass is going to do once you get it hot.
When you're learning, what do you think you're getting better at?
It's learning the process to joining two bits of glass together. When you join two glass bits together, you need them to run what we call a running in process. So we need to create one piece of glass. And that's very, very hard.
Do you get fewer and fewer of those burns as you get better?
Not really. So I'm 22, 23 years in and I still get burnt just as much as anybody.
Do you make pieces for places other than scientific labs?
No, absolutely. So we've made a lot for the film industry. Some of our work has included the Harry Potter movies, the Time Turners in there, and a lot of the cauldrons. The latest ones has been the Beauty and the Beast movie, so we made the wine glasses and we made the cover that went over the rose.
What's the hardest thing to make?
Probably these large reaction vessels, just because of the sheer size and the sheer weight of it. It's not only that, but you get the heat exhaustion. Scott, who makes these, he will, after he's joined the jackets together, he will be covered in sweat and then he will be absolutely tired from the heat.
It's a real art, isn't it?
It is a real art. So we do enjoy what we're doing, just because we have a slight artistic side. Some people do say it's a dying art. However, glass will always have a special place in the science market. It's an inert material. I think there's always going to be a future for glass. If there's science, there's glass.
Ryan Wood there from Glass Solutions, speaking with Phil Sansom.
Chemically speaking, though, what actually is glass and why is it so special? Well, with us is Paddy Royal. He's from the University of Bristol. So, Paddy, put us out of our misery then. This stuff we call glass, which is everywhere, what actually is it?
Glass is an amorphous solid and can be produced from many different materials in the way that ice is a crystalline solid of water and sodium chloride is a crystalline solid, and these are chemically different. Glasses can also be chemically different and are solids, but they are amorphous.
But what actually chemically is the stuff that we call window glass? What atoms are in there?
Silicon and oxygen, so it's 2 oxygens for each silicon, and that is one example of a glass, but there are many other materials that can also be made into glass. Examples include many organic molecules like orthotophenol. You can even make a glass out of water. You have to try quite hard and cool it very, very quickly. To make a glass, essentially what one needs to do is cool it down before the material has a chance to crystallize. So in principle, more or less anything can be turned into a glass, assuming you can cool it down fast enough. Essentially, what we call a glass is when you've taken a liquid and cooled it down until the viscosity has become 1 billion times greater than that of water. And one can do that in principle for any liquid.
Is it true then, Paddy, that when you look at windows of old buildings, they're thicker at the bottom of the pane than at the top of the pane because the glass is a liquid and over hundreds of years it has gently sagged and flowed downhill?
I'm sorry, no it isn't. That is an old wives' tale. The glass did indeed flow, but it flowed as the material cooled. So as we just heard, glass is a liquid at 1100 degrees Celsius, and it is during the cooling process from that temperature down to room temperature that the flow occurred. At ambient temperatures, glass is every bit as solid as any other solid that one might encounter. So there is no meaningful flow or deformation of the material on the timescales of centuries.
From you as a scientist, what is the interest in glasses for you? How are you trying to study them and understand them better?
The real question about glass, as far as we're concerned in glass physics, is we don't really know what glass is. That might sound strange because one can simply look at it, but fundamentally we don't understand why these liquids become so viscous. They become 1 billion times more viscous than water, as I said, but why does this happen? And the truth is that we just don't know. It may be that it happens because there is an underlying material which is known as an ideal glass, and that the transition to this underlying material may result in the liquid becoming very, very viscous and us terming it a glass. On the other hand, it may simply be that the mobility, the amount the particles move or molecules move in the liquid, simply becomes less and less and less. And so essentially there are two competing ideas. There are very many different theories, but they boil down to these two competing ideas that either the molecules somehow move less and less and less, or that there is some underlying transition to something called an ideal glass.
Paddy, thanks very much for joining us to talk about your work. That's Paddy Roll. He's at the University of Bristol.
Now, I'm probably not alone in my absolute love of stained glass. I love going into churches just to look back outside again through those windows. But what is it that makes it so beautiful? I had to find out. I have always loved stained glass. How vivid the colours can get when the light streams through it. But what makes stained glass stained? How does it get that way? To find out, I visited the absolutely stunning stained glass at Cambridge's Jesus College Chapel, along with Jeremy Baumberg from the Cavendish Laboratory at the University of Cambridge, who explained the physics to me in the light of something truly beautiful.
Staining is actually, they added something to the glass when they were making it, and it was discovered, in fact, by the Romans accidentally several thousand years ago. So there's something in the glass which gives it the colour, and that's actually tiny chunks of metal.
What kind of metal, and how tiny?
So the scales we're talking about are billionths of a metre, about a thousandth of a human hair across. And so they're made by, chunks of atoms, maybe 100 atoms across, a bit bigger than that. These chunks of metal behave very differently than when you have a big chunk of metal. So metal's like gold. I have a gold bar. Imagine chopping my gold bar into little bits. So gold looks golden. But at a certain stage, it stops looking golden. But I have to chop it down very, very small. And that size is about the scale of the wavelength of light. So a millionth of a metre. Once I go smaller than that, the way that the electrons in the gold interact with light changes, and I start to see colours.
Stained glass can hit every colour in the rainbow, though. What's the difference between a regal red and a blinding blue?
The interesting thing is if I change the shape of my chunk of gold, I start to get a different colour. So if I just put in a spherical chunk of gold into my glass, then it looks red. Typically, when I look at it in a stained glass. If I'm looking at scattered light, it looks green, so I get some strange sort of iridescent properties to it. If I change that from a sphere into a rod, it would actually go deep blue. And if I actually change it into plates, I get a greeny colour as well. If I use silver, again, I get a different colour. And copper. So gold, silver and copper were some of the main metals used because when they go into the glass, they give you these tiny little chunks of metal. So you don't actually you don't pour liquid metal into the glass. What you do is you put in some oxides of the metal, so ores that you dig out of the ground, which are purified. And during the firing of the glass, the ions of the metal start to stick together and start to form these tiny chunks. And it's the way that they do that is the skill of the glass maker to actually create these different really luminous colours that we see in all the churches and chapels around.
Jeremy, though, doesn't spend his days looking at stained glass, as lovely as that would be. How do we apply this kind of thinking today?
The same properties that the light interacts really strongly with the metal is why it's interesting for us now. So some of the projects we're, for instance, trying to do are to use two tiny chunks of metal which come very, very close together, and then light gets trapped into the gap in between them. The light's trapped in a very small region, so it allows us to look at very small numbers of molecules. So we can use it for sensing. So in fact, we're trying to pour these same metal nanoparticles into toilets to actually make an intelligent toilet that can tell if people's brain state is working well or what dosage of antipsychotics or antidepressants they should take. So that's, if you like, on the biomedical side. Another thing we're trying to do is to make colour-changing wallpapers. So just as these colours can actually colour stained glass, we actually can make wallpapers out of them now, but we want to make them change colour. So you flip a switch and your building turns from red to green. So nobody's been able to do that. The Romans would be aghast if you could take their stained glass and flip a switch and then we could change all the colours. But that's what we're trying to do, and it's the same principle. We trap the light very close to the metal, and if we change the properties of the materials just around them, then we can change the colour that's scattered.
Now the Romans, they didn't know they were at the forefront of nanotechnology. They were just mixing stuff and it worked. So today, how do we go about making these things?
Even a professor can do this in a chemical lab. So actually I brought some with me. So here's a little bottle. This is actually, I made it a couple of years ago and it's still the same. And again, it looks a bit like, weak stained glass, doesn't it? So the way you do that is you take a metal salt and then you reduce it. So you add a chemical which will actually add electrons to the metal or take them away. In this case, it takes them away, so they become neutral. And what that starts as an aggregation, and these little tiny seeds of metal, they start to grow. The trick, however, is to get them to grow in the right way and to all start growing at the same time. So if you can imagine, it's like a whole load of little tiny chunks of metal, and they all start slowly growing together, and then you stop it when it reaches the right size, or you've used up all the metal ions in solution. Even though it's using gold, there's only a tiny amount of gold in this bottle here, and it already gives a very strong colour. So the interactions with the light are very strong, so you don't need much gold to do this.
Jeremy Baumberg there, taking me through the joys of stained glass.
Now, we don't usually think of glass as being particularly tough. In fact, our opinion is usually that it's the opposite, fragile. But can we make our glass tougher? And can we even make it bulletproof? And if so, how? Well, James Perry from the University of Cambridge looks at this kind of science and is here to help us out. James, welcome to the programme. First of all, why is glass weak in the first place? If I take a piece of glass and I lob something at it, like a stone or something, I can smash a window. Why?
So it turns out that the theoretical maximum strength of glass, if you could decide exactly where you were putting all of those atoms of silica and oxygen, is about 1,000 times stronger than an actual lump of glass. Brittle materials, and glass is a prime example of this, their deformation and their failure are largely driven by flaws, imperfections, and particularly cracks. So as you cool a material down, it shrinks. So when you're cooling your glass, it shrinks down and the surface of it looks a little bit like a dried up pond with cracks all over the place. So cracks are particularly problematic in tension, or if you bend a material. So if you take a plate of glass and you start to bend it, the outer edge is in tension and the inner edge is in compression. The outer edge, as you pull it, a lot of the force, a lot of the stress gets concentrated at the very tip of those little cracks. So all of that force is concentrated on just one atomic bond, which eventually will pop open at a much lower stress than it would take to expand the whole thing.
It's going to undo like a zipper, isn't it? It's almost going to propagate down into the material. So once it gets started, it's going to accelerate.
Precisely.
And you said something interesting, because you said when it cools down, you end up with the outside is going to cool a bit faster than the inside, and that's going to have the effect of making those pond wrinkles, as you say, because you'll get the outside being relatively stretched and the inside squeezed a bit. Is there any way of intervening to change that then, so that we don't end up with the glass being vulnerable in that way?
Yes, very much so. So if we go back to the 16th century, there's a fun little thing that came across the Royal Society called Prince Rupert's drops. So if you take a blob of hot molten glass and drop it in a pool of water, it freezes and it turns into essentially a tadpole. And that tadpole you can whack with a hammer on the head, or you can even shoot a lead bullet at it and it won't do anything. But if you just tweeze the tail with your fingers, it will immediately shatter into a million tiny pieces.
Why?
So, skip forward a couple of years to the turn of the last century, and we realised that by cooling very rapidly the material, and for toughened glass now, we use high-pressure air instead of water, you cool the surface very rapidly and that cools. And then the inner bit cools much more slowly. But as it cools, it also reduces in volume. And so it ends up pulling the outside edges in, leaving it in the middle in tension and the outside in compression. And that stops a lot of those little cracks of the surface from opening up, which means if you're then loading this toughened glass, then it's got to overcome the compression that's already under and then the tension required before it'll fail.
So why does nipping off the end break it?
This toughened glass that is used for things like shelves or anything else you might find in the house that you don't want it to fall apart at a smallest knock. The problem is it will fail, and it will fail really quite catastrophically, because as soon as you break through that layer and you manage to tweak the tensile bit in the middle, it pings apart. So in the drop, the tail is so thin that outside compressive layer is incredibly thin. And so you're firing these cracks right the way through from the tail up to the top. So the same kind of thing happens with toughened glass, in that when it smashes, it pulverizes into thousands of tiny little cubes, usually, which in some applications is really useful, because you don't end up with big pointy shards. You end up with a pile of little
like a windscreen does. You don't want to impale the driver. You want little bits of glass you can brush off.
Precisely. But that's not so useful if, for example, you want to be able to still keep that barrier intact after that initial impact.
In other words, bulletproof glass, because you want the glass so that it will not fail in that catastrophic way across your whole windscreen, and somehow also be there as a defence against the next projectile, because otherwise you could kill someone by firing two bullets, one to demolish the windscreen, and it might fend off the first bullet, but if the whole thing smashes to pieces, you fire the next one and it goes straight through. So how do we stop that? How do we toughen up glass?
Above a certain amount of force or a certain amount of stress, you are going to cause some damage. You can't get away from that fact. So the trick then is to build your material such that a single impact of that amount of damage isn't going to completely catastrophically destroy your material. So you can do that by building up in layers. The first layer is glass, which is very, very strong. And so that will help dent the projectile and soften it up. So it goes from a very pointy tip to a much flatter tip. The energy of a bullet is not actually very much, but it's very focused on a small area. So if you can distribute it out, then it's easier to slow down. And that's where the second layer comes in. So behind it, you put a polycarbonate, usually a plastic, which is very soft but very tough. So it can deform an awful lot and absorb an awful lot of the energy in the process of doing so. So what's an interesting thing, actually, to finish on, is the fact that you can have one-way glass. So if you have a layer of glass followed by a layer of polycarbonate, the glass flattens the bullet, the polycarbonate catches whatever's left. So what's a nice illustration of this is the fact that if you're firing in one direction, you hit the glass first, that flattens the bullet, and then that moves into a polycarbonate layer, which then absorbs the energy. If, however, you're firing back in the other direction, you first punch straight through the polycarbonate layer, hit the glass layer, which then fails in tension and spalls lots of small fragments of glass.
So James Bond could, if he wanted to, shoot some enemies from inside his car, and his bulletproof glass windscreen will allow him to do that, but as long as he doesn't shoot first, then it's going to fend off any of the enemy's bullets.
Yes, so long as you put your glass in the window the right way round.
Yeah, if you got it the wrong way round, that wouldn't work, would it?
Indeed.
Does it really work? Can you really fend off a bullet with glass, or is it there really to stop your windscreen demolishing with a stone or something, but not a bullet?
Yes, so possibly a better description would be bullet-resistant plastic with a bit of glass. So for a start, these things are pretty thick. You can have them up to a couple of inches thick. And so obviously an awful lot of energy can be absorbed. It's worth pointing out that, to use the James Bond analogy, I think it was Tomorrow Never Dies, has a car where the bad guys are trying to break into it using hammers and bullets, and absolutely nothing happens to the surface of the windows in the car. That is not the case. You will cause some damage relatively easily, but it'll take a lot more effort to damage all the way through those multiple layers in order to get inside.
James, thank you ever so much for coming in and sharing your wisdom and telling us all about it. That's James Perry from the University of Cambridge, and thanks to our other guests this week, you heard Jeremy Baumberg, Paddy Royal, Ryan Wood, and the folks at Glass Solutions. You have all together helped to open a window into the world of glass for all of us.
And we just have time for Question of the Week, where Mariana Marajoyu has been looking into this nail-biting question from John.
I'd like to know, if enough people in the world donated their finger and toenail clippings, could enough keratin be produced to satisfy the demand and thus stop poaching of wild animals in Africa?
Keratin is the substance that makes up most of our hair and nails, but it's also the substance that makes up rhino horn. This is different though from elephant tusks, which are just very long teeth. The horn of the rhino is the main reason why they are under threat from poaching, and unfortunately they are killed illegally in Asia as well as Africa. To answer John's question, we talked with a couple of experts about this. John Taylor from Save the Rhino International, a large wildlife conservation organisation that works to protect rhinos from threats such as poaching and habitat loss, explained that we first need to understand why people use rhino horn.
The demand for rhino horn is based on many factors, of which its chemical composition of keratin comes some way down the list. In Vietnam, the owning or giving of rhino horn is seen as a status symbol by some people. And research has shown that artificial substitutes or even horns from captive rhinos are not seen as having the same panache. So certainly presenting one's boss with a box of other people's toenail clippings probably wouldn't have the same impact, unfortunately.
I also spoke with Simon Hedges, who works at Asian Arcs on creating protected areas for wildlife in Asia. He mentioned that introducing substitutes to rhino horn might in fact have negative consequences.
Selling alternatives to wild rhino horn, such as synthetic rhino horn, which has also been proposed, or keratin from human nails, undermines vital efforts to reduce the demand for rhino horn in Asia. This is because actively marketing the alternatives would help legitimise the demand for and consumption of rhino horn products, including premium wild source products.
And so the demand for rhino horns might actually increase.
What is needed to address the rhino poaching crisis is effective protection of wild rhino populations and properly designed demand reduction work based on the principles of behaviour change campaigns, not just simple awareness raising, together with deterrent penalties for those trafficking and selling rhino horn.
Thanks Simon and John for your thoughtful answers and for looking after the rhinos. Next time we'll be answering this question.
Hello, this is Julie from Australia. I have received such conflicting advice from TV cooks regarding when to refrigerate cooked chicken. Some say that cooked chicken should be allowed to cool down to room temperature before refrigeration, whilst others say to put the hot cooked chicken into the refrigerator immediately. Which is right?
So what do you think? You can email chris@thenakedscientists.com, find us on Facebook, tweet @NakedScientists, or join in the debate on the forum, thenakedscientists.com/forum.
And that's it for this week. Thanks to Adam for doing a great job putting the programme together. Next time, we're going to be exploring the world of gene therapy, including treatments for macular degeneration and muscular dystrophy. And we'll also hear from a scientist with a potential cure for HIV. Yes, you did hear that correctly, so tune in next time to make sure you don't miss it. The Naked Scientist comes to you from Cambridge University and it's supported by Rolls-Royce and the EPSRC. I'm Chris Smith, thanks for listening, and until next time, goodbye.